Alrighty, so to give you a bit of, this is just a bit of a slide that I suppose outlines how I'm going to go about this talk, I guess. Pretty obvious the importance of nitrogen management to our cropping productivity. Obviously what we're looking to do is maximise our productivity per unit of nitrogen that we put in. As Ash mentioned, if we're losing nitrogen from the system, we have a potential impact on both the environment and everyone's hip pocket. The environmental side of it obviously is something that's attracting more and more attention over the years, particularly when we're talking about greenhouse gases like nitrous oxide and the like. Examples like nitrate of leaching is another one that, leaching of nitrate, another one that environmentally can be an issue. And obviously, as I mentioned, we pay a lot of money to put nitrogen in the system. We don't want it just leaving our paddocks and heading off to someone else's paddock or up into the sky. And yeah, I guess the challenge, and it's always easier said than done, but the challenge is to try and better match our nitrogen supply to the crop demand so that we can really get it in when the crop needs it, get it into the crop and avoid losing it elsewhere. All right, so I guess how efficient are we? This is just a bit of a broad overview, I guess, in terms of our fertiliser use efficiency, some data from 2005. As you can see there, it breaks the world up into a number of regions. We've got an average on the end here as well. What we've got is basically typical cereal yields for different regions, typical nitrogen fertiliser rates, so kgs of N per hectare, and this figure here, this what they call partial factor productivity of N. Basically what that means is how many kgs of grain are we growing per kilo of additional nitrogen that we're putting onto that crop. So in terms of Australia, which comes under this sort of Oceania area, you can see that we're somewhere, in terms of our actual efficiency of utilisation of that fertiliser N, we're somewhere around the world average, pretty similar to North America. But the other interesting one is you can look at places like Africa where their efficiency is through the roof. So what's potentially driving that? You can see they're relatively low yields and quite low nitrogen inputs as well. So I guess where they're at on that nitrogen response curve, they're putting in those low rates, so they're getting really, I guess, big bang for their buck for that first sort of bit of input, whereas in our systems we're probably further up the curve trying to chase those high yields and things, where our efficiency starts to taper off somewhat. So I mentioned nitrogen supply and losses in terms of, like I say, economics and also the environment. This is just a bit of hopefully a simplified diagram. I know it's not completely simple, of I guess where our major N inputs and also some of the potential losses are for our systems. So for me, the key ones are in terms of nitrogen forms, are ammonium and nitrate. They're our two plant available forms of nitrogen. In terms of where we can actually source some of this nitrogen from, so we can source or add to the ammonium pool of soil N through fertilisers like urea, MAP, etc. Mineralisation of organic matter, so nitrogen that's tied up in organic matter being mineralised and made available to the plants. And of course, certain fertilisers where we can actually directly add to that nitrate pool as well. Once we've actually got our nitrogen in there in the ammonium form, there's a couple of different ways it can go. It can potentially be nitrified to nitrate. If it's, for example, if we've top-dressed urea or something like that, and we've got ammonium sitting on the surface of the soil, we can potentially see ammonia volatilisation. We're actually losing some of that nitrogen as gas, as ammonia gas. When we actually undergo nitrification to nitrate, we actually lose a certain amount of that nitrogen as nitrous oxide. Once we've got it into the nitrate form, one of the options it can then leave the system is through denitrification, which is probably where we start to see a bigger risk of nitrous oxide emission. In this instance, so it can be lost as nitrous oxide, as I mentioned, and under certain conditions it can actually be transferred all the way through to N2 or dinitrogen rather than just nitrous oxide. And of course, when we've got nitrogen in that nitrate form, we also can potentially lose it through leaching out of the root zone. You know, when we're having heavy rainfall, irrigation, things like that, and we've got water moving beyond the root zone. Basically, all of these processes depend, you know, if you say, well, how big are they or how small are they, the answer is it depends. So it'll depend on soil, water, carbon, pH, temperature, how much nitrogen's there to begin with, how much rainfall and irrigation. Ammonia volatilisation, for example, as I mentioned, you know, if we've got our nitrogen sitting there on the surface in that ammonia form, and we're not getting good rainfall to wash it in, that's particularly on alkaline soils. That's where we can start to see more volatilisation. If we look at denitrification, for example, though, we start to see larger denitrification events when we've got really high soil water conditions. So, you know, prolonged periods of really waterlogged conditions is where we start to see denitrification kick in. And as we basically get wetter and wetter, what we start to see is instead of producing as much N2O, we start to see that complete conversion through to N2 instead. And yeah, obviously, as I mentioned, nitrate leaching, for it to actually leach beyond the root zone, we've actually got to have water moving outside of the root zone to take that nitrate with it. So as I mentioned before, the ultimate aim, I guess, is matching nitrogen supply to crop demand. So we're all reasonably familiar with when, I guess, peak nitrogen requirements for our winter crops are. You know, it's going to be in that late winter and through spring period, when the crop's really growing rapidly and looking to take up as much nitrogen as it can. Now, in theory, if we look at the sort of seasonal dynamics of nitrogen in the soil, I guess it's kind of handy in some ways. That's also when we start to see increases in our nitrogen supply from mineralisation of organic matter. So essentially what we're looking at during that sort of late winter, spring period, we're seeing soils that are starting to warm up, soils that are still moist, etc. So provided that nitrogen is there in the organic forms, we can actually start to see a bit of a ramping up of that mineralisation supply. So in some ways, I guess the soil is somewhat mimicking the requirements of the crop, which is handy from our perspective. But as I'll show soon, you know, exactly how much nitrogen is mineralised in a given year and things like that can be quite variable and dependent on a range of other factors as well. So this is getting into some of the data of, yeah, I guess what we've found so far. So one of the things that we've been doing over the last couple of years is actually looking at using what we call labelled fertilisers and actually measuring how much of our fertiliser that we're putting onto the paddock is actually ending up in the crop, how much is ending up left behind in the soil, and how much is being lost from the system, if you like. So what I've got here is just some data from Taylor's Lake for 2012-2013, which is just near Horsham. What we've done here, we've just got two treatments just to simplify it. On the left-hand side of these two graphs is where we've put 50 kgs of nitrogen as urea deep banded below the seed, so application at sowing. And on the right-hand side we've got a top-dressed treatment, so urea that's been top-dressed, again rate of 50 kgs of N per hectare, and that's been top-dressed just before first node of that wheat crop. Okay. And basically what you can see here is for that 50 kgs of N, how much of it has ended up in the soil, how much of it has ended up in the crop. And we can see that gap there between 100 and wherever the top of that line is. That's basically how much of it we couldn't find at the end of year. So that nitrogen's been lost to the system, so lost from the system. So what do we see? Generally we're seeing a bit of an improvement in our recovery of nitrogen where we're putting it out during the season, which is a positive. In 2012 it wasn't necessarily a significant difference, but 2013 it was. We're seeing, somewhere around about 40 to 55% of that nitrogen that we're putting out actually ending up in the crop, which is where we want it, I suppose. And we're seeing differences between different seasons as well. So we can see in 2013, the difference between those two treatments was a fair bit larger. What our theory at this stage at least is that 2013 we probably had a slightly wetter winter. In some ways we may have actually been getting... Sorry,
confusion. Yep. The left-hand graphs are the banding and the
yep.
right-hand graphs are the numbers.
Top dressed. Yep, sorry. That's the one. So at this stage we've got a lower recovery in 2013 where we put it out at sowing as opposed to putting it out in season. Our theory at this stage is that that earlier application we may have been getting some denitrification going on, whereas the later application we may have sort of avoided some of those really waterlogged conditions that we got through the winter. So I shouldn't say really waterlogged, but somewhat waterlogged conditions that we got through the winter, and hopefully avoiding some of those losses. Just for comparison's sake, this is some work colleague Rob Harris down at Hamilton has been doing, so sort of it's the same project really, but very similar work to what we've been doing now. In this case, Rob's treatments were a bit higher nitrogen rates, so instead of 50 kgs of N, he's been putting out 100 kgs, which is, I guess, just reflective of their general yield potential in that environment as opposed to our own. Again, on the left-hand side where we've put it out at sowing, and on the right-hand side where it's been top-dressed around first node. And I guess what we see here is far more pronounced differences between where we're putting it out at sowing and where we're putting it out during the season. So, and in fact, I mean, if we look at these in-season, pre-sowing treatments, if you said to someone that they're putting out 100 units of nitrogen and you're only going to be able to find 10 to 20% of that nitrogen come the end of season, it's not overly impressive. But certainly the good news is, I suppose, with those in-season applications, they were getting pretty good recovery rates, and a fair bit of it was still there, and certainly the majority of it was in the crop, at least in 2012, which is where we want it. So naturally, again, asking the question, well, where's that fertiliser actually going? One of the things that we, in addition to this nitrogen recovery measurements that we've been taking, we've also been actually monitoring these sites for nitrous oxide loss. Basically looking at Rob's data set, in the grey line here we've actually got what we call water-filled pore space, which is essentially how waterlogged is the soil, how many or what percentage of that soil's pore space is actually occupied by water. So as we're getting up around this sort of 60 to 80% water-filled pore space, we're getting pretty wet sort of conditions. So if we look over the season from April, June, July into August and September, we can see where that soil water conditions are really peaking during the year. And if we look at these daily nitrous oxide losses, I know this is a hard scale to read, but that's actually kilograms of nitrogen per hectare per day being lost as nitrous oxide. So essentially, if we look at that peak there in probably early October, late September, somewhere roughly 350 grams of nitrogen there that's been lost in a single day as nitrous oxide. So I guess they're pretty high numbers when you look across other published data sets and the like, they're certainly not small numbers. And I'll show you some of my data from Horsham in a tick, which will back that up. So I guess what we're thinking here is that when we look at these, really poor recovery rates from where that nitrogen's been put out earlier in the season, we may well actually, part of the explanation there may be from denitrification events. And as I mentioned, corresponds reasonably with where our water-filled pore space is suggesting that we're quite sort of waterlogged. Certainly from a productivity perspective, if I look at my own situation around Horsham and that, I don't think we're seeing a productivity impact of that nitrous oxide loss. But as you said, nitrous oxide is a potent greenhouse gas, and therefore, we can have a relatively smaller productivity impact, but it sort of multiplies out a lot more when we look at it from an environmental impact. But look, ultimately, I guess what we're looking at here is a system that is prone to nitrous oxide emissions. We're getting pretty reasonable sort of numbers. All of the indicators are suggesting we've got a potential for high denitrification events. To contrast that with our data from Horsham, up the top here, this is just data from 2013. In red, where we added 50 units of nitrogen at sowing, versus in blue where we put out no nitrogen. The bottom graph, we've got daily rainfall totals, our soil temperature in red, and our soil moisture content in green. Again, you can see where we've added the additional fertiliser. We've generally throughout the year seen a slight increase, particularly through that winter period, a slight increase in emissions relative to where we haven't put fertiliser. Certainly once we get out to the late spring and summer periods, it all seems to have sort of disappeared, I guess, those differences, and we're getting back to these sort of background level of emissions in some ways. But the really important one is just to look at the magnitude of these emissions. So this is no longer kilos of N2O(N). This is actually grams of nitrous oxide N per day. And we've gone from a situation where we've got peaks that might be 350 grams of N in a day, and our peaks are typically well under 10 grams in a given day. So I guess that's the main point, is looking at, we've got one system which is sort of almost like nitrous oxide on steroids in some ways, and then in the other situation we've got a much lower level of emission. So and as I said before, this is about things like soil water. We're not spending those large periods of time in a waterlogged state. Our background mineral nitrogen levels are not as high as well. We also have nowhere near the levels of labile carbon available in the soil. They're probably three of the big ones there. So that probably leads me into this next slide. Well, why the difference? Essentially I always think of it like a lever, and you can have one half on, half off, all the way on, all the way off. As I mentioned, soil water, so soil type, rainfall, irrigation, depending on that, the propensity of that soil to actually hold on to that water and stay in a waterlogged state is going to have a big impact on this. What are our background nitrogen levels? If we haven't got nitrogen there in the first place, well, we can't lose it. Soil carbons, so these processes are soil microbial processes. They're driven in part by our level of carbon in the soil. Likewise for temperature, these guys have a certain temperature that they prefer. Generally warmer is better to a point. And pH can also have an impact as well. So just a couple of those big ones, and I've sort of already alluded to a lot of this anyway. Sort of comparing the high rainfall Hamilton and Tarrington sites versus the Horsham Taylors Lake sites in 2012 and 13. So as you can see, a fair bit more winter rainfall down south, but multiple times the level of soil organic carbon, sorry, SOC, soil organic carbon in the topsoil. Yeah, so a lot more labile carbon there available to contribute to that mineralisation and also to those processes that are resulting in our N2O emissions and such. So yeah, I guess coming across here today, I thought, well, what about irrigated crops? And in theory, yeah, if we're looking at irrigated situations, we've got a bit of a greater potential for some of these emissions and also for nitrate leaching outside of the root zone. And the other thing that can be worth remembering too when we're looking at irrigation, well, any situation really, but irrigation can be a little bit more of an issue, is around re-wetting cycles. So one of the things that has been observed in some cases is that when we have a situation where we've got a dry soil, undergoes an initial re-wetting. So let's say if you're you know, in a dryland situation and you get a big dump of summer rainfall, or alternatively, yeah, if you're in an irrigated cropping situation and you're putting in a summer crop and you're irrigating for that summer crop, that initial re-wetting process can actually produce quite a spike in emissions as well. So it's handy, we actually do have some data from irrigated situations. We've been working on a project the last couple of years with the Irrigated Cropping Council. So what we've got here, yeah, again, is N2O fluxes for two different nitrogen rates for an irrigated maize crop that was grown last summer. So yeah, sown back in December, and we monitored for emissions right through to March, and basically you can see the magnitude of these losses there, where our losses were topping out around 5 grams per hectare per day. Rob's were up around 0.35 kilos. In this case, you know, we've got numbers that are just bigger again, I suppose. To the point where I actually sat down and looked at these numbers and I thought to myself, are they real? But anyway, yeah, in some of these cases we may well be seeing quite high sort of daily loss rates. So yeah, we've talked a lot about nitrous oxide emissions and the like. Essentially, one of the things I just wanted to point out, we've already talked about the importance of waterlogging for nitrous oxide emissions, but the other one to keep in mind is that dinitrogen N2 losses can be quite high. You know, it can be up to 50 times whatever you're losing as nitrous oxide under the right conditions. So it can be a risk if we are getting those big waterlogging events, particularly if they hang around for a while. Volatilisation can be a real problem if we're top dressing. You know, we don't get that follow-up rainfall, alkaline soils and the like. We can lose a bit to volatilisation, and leaching is another one to consider as well. So, as I mentioned before, we're looking at matching end supply to crop demand, and I think we started to sort of talk through some of these principles already, but basically what we're looking at the moment is a process where understanding how much N we've got there at sowing, having some sort of an estimate for the season of how much we might be able to supply from mineralisation of organic matter, and the third one, understanding exactly what the crop, the ability of that crop to actually uptake nitrogen is. And this is actually leading us into our new project with the North Central CMA, which we'll start to plug a little bit now. So in terms of predicting nitrogen mineralisation, this is just some work that a colleague of mine, Catherine Dunsford's been doing as part of her PhD. Basically what she's been looking at is the potential for mineralisation of nitrogen under different rotation scenarios. And this is actually built on our, what we call SCRIME, which is our long-term rotation trial at Longrenong. It's been going for 25 years. And what we've got here is just a comparison of a handful of different rotations and their actual potential for mineralisation their mineralisation rate during 2012. So, for example, if we look at continuous wheat, and we skip right over to this side of the table, just to speed things up. Basically, that continuous wheat rotation in 2012, we were looking at a mineralisation of about 26 kgs of nitrogen per hectare. If we compare that to rotation 8, which is a loosen, followed by canola, wheat, pea rotation, we've got significantly higher potential for mineralisation of nitrogen in that system. So, yeah, obviously in that case we've got the legumes there contributing to more nitrogen supply, and potentially seeing that mineralised in that first season. So I guess the point of that is that, it's that whole soils ain't soils thing, and thinking about the individual situation and the potential to supply nitrogen in that given situation. I've just got a question there around, mineralisation, is it actually enough to meet crop demand? Well, yeah, again, that'll be highly dependent on the situation. We can see if we are getting those sorts of rates of nitrogen mineralisation, and that's in some of those cases, if we're not yielding too much, well, potentially yes, but in a lot of other situations we might not be. As I mentioned before, so yeah, we've got mineralisation. We've also got the question of how much nitrogen does the crop actually require? How much can it actually uptake in a given year? Now, historically, I guess our rule of thumb that I was always taught, at least, was that to grow a tonne of wheat takes about 40 kgs of nitrogen per hectare. So, but those rules of thumb are generally based on an uptake of about 50%, so assuming that 50% of whatever fertiliser we put out in a given year actually makes its way into the crop. But as we can see from our fertiliser recovery data set from down at Hamilton, we can see really big differences in terms of how much of that applied N actually ends up in the crop in a given year, depending on the situation. So what have we got? We've got a handful of gaps in knowledge which we're looking to address with this project. One of them is around some new methods for actually looking at potential mineralisation and estimating how much we might be able to supply from mineralisation during the year. Understanding at a local level what's a sort of relevant ability of that crop to uptake our fertilisers. And as I said, hopefully that contributes to enabling us to actually do what I said earlier, which is better match our supply to our demand. So what are we doing? Getting into the specifics of the project. Basically, we've got sites set up across a range of rainfall and cropping systems, looking at different soil types, environment, looking at recovery of N fertiliser like we have in the past, looking at N2O losses. As I mentioned, the greenhouse gas side of things is an important one, and also looking at mineralisation and some of those alternative tests to help us estimate what our mineralisation might look like. So in terms of where the sites are located, we've got 3 sites in the Wimmera around Longanong and Taylors Lake. We've got 3 down in the Glenelg Hopkins CMA around Hamilton, high rainfall country. We've got 2 irrigated sites up here in the north central region, and one out at Normanville on the edge, that sort of, I guess, low medium rainfall type situation. This is about the only data I'll show you for this particular project at this stage. I guess just looking at the actual background levels of nitrogen and carbon in those particular situations. As I mentioned, we were looking for a spread of different situations so that we could, start to nail down some of these research questions. So if we look in the green, these are our 2 irrigated sites. Our carbon and nitrogen levels a bit higher than what we've got in red, which are our medium and low rainfall situations. But certainly in terms of our carbon and nitrogen levels, outstripped by a fair way by those high rainfall high rainfall sites around Hamilton. Our trial design at each one of these sites is pretty simple. We've got 9 sites, so we can't have it too complicated. We've basically got a simple little nitrogen response trial at each site with 2 different nitrogen rates and a control. We soil sample pre and post season so that we know how much is there pre-seeding and also how much has been left behind at the end of the season. As I mentioned, we're still looking at nitrous oxide and weather. We're also looking at, of course, the crop response to that nitrogen. So again, you know, if we're looking at different management options, we've got to understand their productivity impacts, otherwise there's not much point. And we're continuing to measure that recovery of applied fertiliser in these different situations and testing out a few of these potential mineralisation lab analyses. So, trying to finish up there, just a few key messages. Basically, as I said, our losses and our inputs really depend a whole lot on our soil type, our environment management, etc. And what we're trying to do is better understand the interaction between those. Predicting mineralisation can be difficult, but can be really important. I mean, you saw the data there from that long-term trial. It'd be very easy if we went in with a blanket estimate of mineralisation across that situation. You know, it could be very easy to sort of blow the crop up and hay it off and put out a whole lot more nitrogen than we really needed to, or alternatively not put on enough. And everyone always talks about the 4 R's approach. You know, right rate, right time, right product, and right place. And again, this is another one of those statements. It's always easier said than done, but essentially what we're hoping to do with this project is help to contribute to actually being able to achieve some of those 4 R's. And of course, I've got to say thank you to our host farmers. We can't do any of this work without them, and all of our collaborators, including GRDC as well, who've funded some of that previous work that I alluded to. So, and thanks for listening.